And that is what we call Hess's Law, thermochemistry. All right, so continuing our Hess's Law work. Sometimes we see examples like this. They say, hey, here's 3 equations. A plus B produces X, requires 10 kilojoules of energy. B plus X produces C, requires 5 kilojoules. And C plus Y produces Z, and will release 8 kilojoules of energy. Given this information, can you tell me how much energy is absorbed or released when A reacts with C to produce 2X? And so this becomes another question of where's the energy coming from? Just like on the previous example of Hess's Law, when we're summing reactants and products, we're going to do that, but we're going to articulate it in a different way. We're going to say, well, each of these reactions has energy. This reaction can be expressed as a combination of these other reactions, and that'll allow me to find this energy. So let's take a look. We want A on the left as a reactant. It already is here, so that's a good sign. We want 2 X's on the right as products. Here's 1, so that's a good sign. I have 1, but it's over here, and if I add these equations together right now, this will look like when we have like spectator entities or whatever. It'll cancel out if it's on the reactant and product side. It won't be part of the reaction. So what if I wrote this one the opposite direction, right? What if I flipped it? So if I flipped it, I'd have C producing B and X. But if I flip it, it makes sense that my delta H should also get flipped. This is me multiplying this equation by -1. I'm flipping it. So reactants become products, products become reactants, and my energy change is now different. Instead of an endothermic reaction, the reverse is now an exothermic. Now it doesn't matter if this reverse reaction is what we call plausible. Excuse me. It doesn't matter if this reverse reaction is plausible. All that matters is that mathematically, these entities will line up in such a way that it expresses this equation, and that we're treating the energy with the same treatment that we're giving the reaction. If we double it, we have to double this enthalpy. If we reverse it, we have to flip the sign on the enthalpy as well. As long as the math lines up, it doesn't matter if that reaction is physically possible in the environment, because we're not doing the reaction, we're just accounting for where all the energy came from, right? So it comes to this idea. Actually, I'll tell the idea in a second. So if I flip this now, what do I have? Well, now I have A on that side. Oh, and I have C. I have my A, and now I have my C. Excellent. 2x, now I have an X and an X, so my 2x's are good. And I don't even need this last equation, because look at the B's. I have B's, but now there's a B on either side. So if I rewrote those, I have A plus B producing X, and I'm combining it with C producing B plus X. And again, my delta H is 10 for the first one, and my delta H for the second is now -5. When I add these together, my B's cancel because they're on opposite sides. My X's combine because they're on the same side. Now I have A plus C produces 2X. What happens when I combine these? I get +5. So the delta H would equal 5 kilojoules. That answers our question here, 5 kilojoules. This reaction can be expressed as a collection of these reactions. I didn't need this one. We see we don't always need every reaction that they give us in the problem. And this is now the enthalpy change for that reaction. The idea that I'm talking about is it comes back to this thought that if I'm going from here to here, thermodynamics says because energy is conserved, if I go here, then here, then here, then here, then here, and then here, the change is the same. For those of you who know about physics, Hess's law is similar to that idea of distance versus displacement. The distance here in physics is greater than the distance here, but the displacement is the same. My start and my finish points are the same in both situations. So Hess's law is like displacement. It doesn't matter exactly the activities that take place in these reactions versus in this net reaction that we're looking at. All that matters is the energy is accounted for. So if I can construct this through some variation of these other ones, and I know the enthalpies for these other ones, I can find the enthalpy for this one just mathematically, just by accounting for all these things, trying to make it match. It's a matching game. It's more like a puzzle than anything else. And if you can solve the puzzle, you can find the enthalpy. Let's do another example. Let's say we had an example that said something like, maybe I'll grab my black marker again. If we had an example and it said, you know, A will produce B and C, and it has a delta H of 20 kilojoules. And the question is asking A plus Z produces W plus X plus Y. What's the enthalpy change for this? So same thing, it's a little bit more involved. We're going to look at each step. What do we have? What do we need? So A starts on the left. That's positive. Like that's a positive thing, I mean to say. Z, I have Z in a couple of places, and I don't have D anywhere. Notice how there's no D. I'm going to need to use all these equations though, because I want to use Z, and I want to introduce W, so I definitely need this, but I don't want to keep the D here, so I need to do something about this. How will I get these D's to cancel? Well, they're on opposite sides, so that's a start, but there's 2 here, so I need to multiply this second equation by 2. Okay, let's see what we have so far. Oh, let's add one more step. B and C, I don't have them in my result, in my final goal here. So let's cancel these right away. I want to keep A on the left, so I won't change this one. I'm going to flip the second one. Flip. So remember, if I flip it, I multiply the enthalpy by -1, and this one I doubled, so I'm also going to multiply the enthalpy by 2. We didn't double anything in the last problem, but we talked about it, and then we're going to do it this time. Let's see what we have so far. So I have A, and I have B and C. If I flip the second one, I will have B and C, and I will have X and Y. If I double the third equation, I'll have 2Z, and I'll have 2D. And then if I keep the fourth equation the way it is for now, let's see if that's good enough. What's the result of combining these? Well, B cancels with B, C cancels with C. 2D cancels, 2Z and 1Z. One of these Z's will cancel, I'll have one left over. So I have A, Z, X, Y, W. A, Z, X, Y, W. Super. So now we just go back to the changes we made. We did not change this last equation. I'll write an equal sign, it wasn't changed. We didn't change the top one, but we did flip that one and double this one. So when we sum up the enthalpies, what do we have? We're going to sum up the delta H's. We're going to have 20 plus negative times negative, so it becomes positive, but I'll write it out so we can see that, but it becomes positive. We're going to add 2 times 10, and we're going to add -30. Grab our calculator if we like, so that's positive now. So we have 20 plus 40 plus 2 times 10 is 20 plus -30, so I'll go subtract 30, 50 kilojoules. So if we return to here, the answer, the delta H, would be 50 kilojoules for this overall reaction. So you can see it's just like a puzzle. The problems you're going to get, of course, are going to have actual chemicals in them, but I find it's useful to illustrate just with the letters, because that's all we're trying to do, is make things cancel. We're trying to make things cancel so that we get the arrangement that we're asked for. And again, why does this work? Why does Hess's law work in either of the scenarios? Because the energy has to come from somewhere. And so if the energy is present here and it's all conserved in the formula, or in the reaction I should say, it's all being conserved, it's not escaping somewhere else, well then it doesn't matter, as we say, it doesn't matter the path we take. All that matters is the start and the finish. Again, in chemistry, it's not the journey, it's the destination. I would encourage you to enjoy the journey in your lives, of course, but in chemistry, it is the destination, and that's Hess's law. As always, I'm Braden. Happy to help you guys out. Let me know what you want to see next in your physics, chemistry, or high school math, or pre-calculus, and we'll get it going. Have a good day, guys.